All right, so first let's start to define stress and strain. So we are going to define stress, sigma, and we're going to actually specify this is going to be our normal stress. And by normal, we mean that the force that is applied is normal to the surface that is being acted upon. So what do I mean by that? If I pull my material like this, I'm going to call this a normal stress. And that is just simply there's a force acting on a cross-sectional area here. So that's my basically area A naught here. So this is my definition of stress. It is in units of newtons per meter squared or pascals. This is actually engineering stress. So this area A naught is my initial area. As you deform your system, you can observe necking and other components. And actually, in this stress strain curve, the ultimate tensile strength, this is actually the onset of necking. And necking is when effectively your sample starts to kind of thin. So you're pulling something and then it starts to thin out along this region here. But anyways, aside from that, this is our force acting on a cross-sectional area. It is units of Pascal. So this is our engineering stress. Our true stress would be the instantaneous area, but that's a topic for another course, and we'll be able to get through that. If I am shearing, for example, a system like this in here, this would be referred to as a shear stress. So there's still a force acting, but it is not normal to the cross-sectional area that it's acting upon. It's actually in plane with that area. So that would be your shear stress. You'll see this tau quite often. But the way that we are going to define stress, we need to have a coordinate system. So we are going to, stress is a second-rank tensor property. So it is equivalent, there is a directionality to it. So this subscript I is going to denote the normal to the plane on which the force is acting, and J is going to be the direction of the force. So our system, our coordinate system like so, 1, 2, 3, and our representative volume element, which we're going to act upon in terms of our stress, this is our expression here. So if I have, for example, sigma 3, 3, and you can see I'm going to have a, again, second rank tensor. If we live in a three-dimensional world too, there are 9 components here. So my stress in the 3, 3 direction, so again, I is the normal to the plane that it's acting on. So in the 3 direction here, that would be the normal, anything that's in the 3 direction, it'd be normal to this plane. So we know we're acting on this plane. 3 is the direction, so it'll also be in this direction. And we're pulling essentially simultaneously here. So this would be my sigma 3, 3. What about this stress? What's the normal to the plane here? So that'd be sigma 2. What's the direction of my stress? 2. Now this is positive. If I were pushing down here, our sigma 3, 3, the value would be negative in our stress tensor. Let's do something a little bit more complicated. What about how we actually determine, how do we determine shear stresses? And specifically if they're positive or they're not positive. Well, let's go ahead and let's talk about it. So let's say I have, actually, let me draw this. Let's say I have a stress that looks like this. So what's the normal to this plane? 3. What's the direction here? 2. Excellent. Now, is this shear stress positive or negative? The way that we are going to determine this is as follows. So I am going to we are going to state this top surface, it's acting on this surface and a bottom surface here. So when I'm looking at these surfaces, I'm going to define this as my positive surface, and this is my negative surface. So here, my force was pointing on the positive surface in the positive direction, and in the negative surface in the negative direction. That is going to be determined as a positive shear stress. If it were flipped, so for example, if I drew it like this and this, so on my positive surface, if it's pointing in the negative 2 direction, this would be a negative shear stress. And the same thing here, I'm going to define this as my positive face here, my negative face here, and then my positive face will be out of the board here, and the negative face will be, or actually, the negative face will be into the board there. So those are effectively going to be our, kind of positive and negative surfaces that we're going to define. So you just define those surfaces and then make sure that you're kind of clear on the positive and negative sense of shear stresses. So there's a couple of examples, and we can kind of go through some of them in another section here. So one thing, do we have truly 9 independent components? Well, remember, we need to make sure that the sum, we can put this out here, we're going to put that the sum of our forces, and the sum of our moments must be equal to 0, because we are still in static equilibrium. So let's look at an example of, let's say we have in our coordinate system here, let's prove this is the case. So let's do positive, so let's do sigma 3, 2, and then positive here. And then let's do sigma 2, 3, which will be 2 in this direction, so positive like this, so like this. So this is sigma 2, 3. So if I look at sum of the forces in the 2 direction must be equal to 0, that's going to be equal to, and then we're going to call this little element is like delta 1, this little element, this length here as delta 2, and this length here as delta 3. So if I look at my forces in the 2 direction, it will simply be, so what I was pointing in the 2, so it's going to be this, and then this is going to be positive 2, so that's going to be sigma 3, 2 times the area on which is acting is delta 1 times delta 2 minus, because we're pointing in the negative direction here in the negative 2, minus sigma 3, 2 in the same area times delta 1 times delta 2. So you can see here, this basically says that sigma 3, 2 must be equal to sigma 3, 2. So the forces here, they must be equal in magnitude. And you can do the same thing for 2, 3. Now the interesting part comes, if I define this as my origin, and if I do the sum of the moments about O, I can see that if I look at this force, right? So if I do sigma 3, 2 times the area on which it's acting, so sigma 1 dot sigma 2, and then, so this is my force, right? Stress times an area, because stress is Newton per meter squared times meter squared. So force times a moment arm. So if I look at this force, my moment arm here, from the origin, the O that I'm looking at right here, that's going to be delta 3. And it's going to go in what direction? So actually this is clockwise, so I need to set this to negative. So sum of the moments must be equal to 0. So this doesn't count, this doesn't count because there's no distance between them. And then if I look at plus sigma 2, 3, because it's going to bring me in this direction counterclockwise, and that area that's acting on is delta 2 times delta 3. Let me see, yes. Delta 2 times delta 3. Wait, let me make sure. Actually, no, excuse me. Delta 1, delta 3. And the distance here, from here to this plane, is the delta 2. So that's my force here times my lever arm, delta 2. So what this says is, and this all must be equal to 0, so these cancel, and I get sigma 2, 3 must be equal to sigma 3, 2. So my 9-component tensor reduces actually to 6 independent components. So basically my sigma 1, 2 is equal to sigma 2, 1, my sigma 2, 3 is equal to sigma 3, 2, and my sigma 1, 3 equals sigma 3, 1. So this will be the tensor, and it's basically, it's symmetric. We're symmetric across our diagonal right here. Excellent. So we can draw and write those out. Now, in terms of strain is effectively going to be equal to, or normal strain is just going to be the change in length over my initial length. And that's our engineering definition of strain, and that's observed here. Our true definition will be that instantaneous, basically, the instantaneous length, and that changes as well. Also, you can also see shear strain indicated over here. So your shear strain, and we'll see an example of that, is effectively going to be when I'm shearing essentially our material. So my shear strain will look something like this, where if I have an object, this is my initial object, and then I basically shear it to some extent, and then it, that's horrible. Actually, let's erase that. You can see essentially here a system in pure shear as well. So I'm shearing the system, so there's a change effectively in length here. In the most simple definition, you can kind of see this. So when I have a system that looks like this, and I shear it, so there's some change in my length. We can go ahead and draw that. So this would be my original, and then when I actually try to draw the shear surface, it would look something like this, where I go here, again, just exaggerated, and then like this. So I have some initial length, basically L here, and then there's going to be some change in length, DL here, and you can now, based on this angle here, you can actually calculate that, and this is engineering shear strain. Now, there's one caveat to this. Our definition of engineering shear strain has this pesky half, and infinitesimal strain theory is something that you can read up on, and I have several videos that go into this more in detail for this topic. But if you're interested in this, there's actually the actual really rigorous definition of strain is this infinitesimal strain theory, and you see that our engineering definition of normal strain, so again, when I'm applying strain normal to the area on which it's acting, is exactly the same as this definition. But here, you can see that our tensorial definition, epsilon 1, 2, for example, is equal to gamma 1, 2 over 2. So if you measure engineering shear strain and you put it in this tensorial format, and you see the symmetry here because, again, we have the same symmetry due to the fact that we have to conserve our elastic strain energy, you'll actually see this little nuance there. But again, that's a little bit more for a more advanced course. So, next time, we're going to get into Poisson's ratio. See you then.